So that's the formulas which we got the last time. And now we'll do some derivatives, some integrals using this maybe 4 formulas if you also take into account that antiderivative e to x equals to e to x plus c. As the first comment is going to be, if I want to find antiderivative of 3 to x. So let me try to address that situation. What I'm going to be doing is I'm going to use property that natural log is inverse function of e to x. So it means if I take e to the power ln of x, so it means I'm taking ln and then I'm taking e over it, exponential function, so they cancel each other, so at the end I'm going to get just x. So in particular, 3 equals to e to ln of 3. Okay. So now let's use that and let's substitute that expression for 3 into the derivative of 3 to x. So we wanted to find derivative of 3 to x, and 3 is equivalent to e to ln of 3, and then we multiply by x. And then we'll do chain rule. Our inside function is going to be ln of 3 times x. Outside function is e to x, so we're going to get derivative inside function is going to be ln of 3. And derivative outside, e to the is e to the. And then you recall that e to the ln of 3 is just 3, so we're going to get ln of 3 times 3 to x. So that's going to be our answer for the derivative of 3 to x. So if you like, you also can write that as more general as a formula. And derivative a to x equals to a to x times natural log of a. And the proof will go exactly the same way as we did with 3. Just all that you have to do is just substitute a instead of 3. And don't forget, we always assume here that a is positive. If a is negative, then a to x makes no sense because often x is going to be fraction with denominator, even denominator, so we're going to get like even roots. So we cannot do that. And also on the right side, if you look carefully, you have a natural log, and natural log is defined only for positive numbers. Okay, so that's maybe one more formula. We're not going to be seeing it often because most of the time we'll assume that our exponential functions are going to have base e and a natural base, at least for couples. Now let's do a couple derivatives using natural log. Find the following derivatives. The following derivatives. Say ln of 1 plus x squared. And we want to take its derivative. So here we have inside function u equals 1 plus x squared, outside ln u. So derivative inside will be 2x, derivative outside, derivative of natural log is 1 over u. So we can chain rule, so we're going to get 2x over 1 plus x squared. Natural log of sine x plus cosine x. And I want to take its derivative. Derivative of natural log is 1 over, right? Derivative of natural log is 1 over, we had it somewhere here. So derivative of natural log is 1 over argument. 1 over u as we did in the previous case. And derivative inside function, derivative sine is cosine, derivative cosine is negative sine. And we will write that as a big fraction, cosine x minus sine x plus cosine. That's going to be answer for B. Derivative of x cubed plus x squared plus x plus 1. Okay. So actually, I'm going to give you a minute or two to try to figure out what will be the derivative of that expression. Okay, let me try to catch up on you. So derivative outside function, derivative natural log is 1 over, and we keep this original argument, x cubed plus x squared plus x plus 1. And derivative inside function, derivative x cubed plus x squared plus x plus 1, it's straightforward. 3x squared plus 2x plus 1, if you like, plus 0. And the only thing which I'm going to do with this expression is I'm going to rewrite it as one big fraction. 3x squared plus 2x plus 1 divided by x cubed plus x squared plus x plus 1. Okay. And if you like, you probably already noticed the pattern. So the pattern is the following. So if you want to take derivative of ln of any expression here, then derivative of ln is 1 over, so we're going to write that expression. And derivative is inside is derivative is inside, right? So that's shortcut. So derivative of ln of f of x is going to be f prime derivative on top divided by the function. And that's exactly what you noticed. So for example, in the previous example, you see the derivative on top, you see the original function on board. Same way here, you see derivative on top, function on the board, argument of ln. Say ln of x squared plus e to x and its derivative over original argument, and on top its derivative. And when we're taking derivatives, of course, the rest of the rules will also follow. For example, product rule, quotient rule. Say, I will do example with product rule. If I want to do x squared times ln of cosine x, I'll do product rule. That's my scheme for product rule. And the first brackets, I'll put x squared. In the second, I'm going to put ln of cosine x. And then derivative of x squared is easy. Derivative of ln of cosine x is also easy. If we realize that we already did a bunch of those and we know the shortcut. So the final answer is going to look something like that. And the only thing which you can do here is maybe from a second fraction is to just take negative in front. So it will be easier to read, and maybe we'll rewrite as one big fraction, but otherwise it's about it. Maybe to switch language of tangent, sine over cosine is tangent. I'm not sure, but